All right. So today is one-to-one functions and inverse functions. All right. So go ahead and select us a little marker right with. A function is said to be one-to-one if any two different inputs in the domain correspond to two different outputs in the range. That simply means none of the inputs or outputs can repeat. Nothing repeats. If the inputs repeat, all right, so we have inputs, outputs. Now, if the inputs repeat, then it is not a function, all right? So let's say we input 1, 2, 3. None of those inputs repeat, so far we have a function, even if it goes to 2, 4, 6. Input 1, you get out 2. Input 2, get out 4. Input 3, get out 6. All right? This would be considered one-to-one because none of the outputs repeat. Again, if none of the inputs repeat, then your relation is a function. If none of the outputs repeat, then you have a one-to-one correspondence, meaning the function is one-to-one. All right, let's scroll on up. All right, so rolling through this example, it says determine whether a function is one-to-one. All right, it gives us relation. All right, now going through, you looking through everything, and then you're like, hold up, what's all that double arrow at the bottom? Right here, that's saying that 38 is going to happen twice because 38 will go to 55 and 38 goes to 61. All right, so therefore, this is not a one-to-one function. Not one-to-one. All right. Now let's look at all the values. It said determine whether a function is one-to-one. So it already gave us the pre-notion that these are functions, so we don't have to check to see if they're functions. Let's just look at the output values. 6, 3, 2, 5, 8. No output values repeat, therefore this is a one-to-one function. Okay? Then let's say you wanted to determine if a graph represents a one-to-one function. All right, so the horizontal line test says if every horizontal line intersects the graph of a function f and at most one point, then that function is one-to-one. Without all the math language, it says if you draw a horizontal line, boom, draw a horizontal line. If it hits at more than one location, then it's not one-to-one. That's all that says. All right, so horizontal lines are lines that go to left or right. So if you draw a line that goes from left to right and it hits a graph in more than one location, then that graph is not one-to-one. Here we have the square function as an example, and we want us to use the horizontal line test to determine if it's one-to-one. The square function is a graph of a parabola. Now, if we draw a horizontal line through this, does it hit more than once? 1, 2. This is not one-to-one. It failed the horizontal line test. And then you have the cube function. Cube function. Now the cube function, draw a horizontal line one time. No matter where you draw that horizontal line, it's only going to hit that graph once. So in this case, it's just got one-to-one or not. Good stuff. It passed the horizontal line test because it only hit one time. Therefore, we have a one-to-one function. All right. Now, determine the inverse of a function. Now, If the function is 1 to 1, then it is invertible. And then determining the inverse of a function, hey, it's cakewalk. All you're doing is swapping out the x and y values and then building that thing. All right. So to find the inverse, we interchange or swap the elements of the domain with the elements of the range. The elements of the domain are your input. The elements of the range are your outputs. Domains are your inputs, range are your outputs. So let's do a quick little example here. Let's say we have this function here. We'll call this function f. And we're going to input, or our inputs are 1, 2, 3 again. And the outputs are 2, 4, 6 again. Now, if we want to find the inverse, since this is 1 to 1, if we want to find the inverse function, inverse is denoted by raising a -1 over your function name. Let's make it cleaner. We don't do no halfway work. Alright, so the inverse function, we said to swap the inputs and the outputs. So the inverse function would be, so we have 2, 4, 6, and 1, 2, 3. So what you just, if you look at this, you are telling me that the domain of the original function is the exact same thing as the range of the inverse function. The domain of the original function is the range of the inverse function. And the range of the original function is the domain of the inverse function. I know it sounds real mathy, but whenever you look at it, you're like, oh, okay, I just sound real mathy. I'm getting geeky with it. All right. I remember the first time I saw these blobs of pictures right here, and I was like, what in the world is going on with this? But it didn't register to me with these blobs of pictures. But all these blobs are saying the domain of the original is the range of the inverse. The range of the inverse is the domain. The range of the original is the domain of the inverse. And that's exactly what we did up top in our example. All right. Finding the inverse function. All right. It's pretty easy. Like, this is your original function. We'll just call it f. And the domain of the original function would be the states, and the range would be the populations. Well, if that's the original function, then the domain of the inverse function would be, and you got it, the population. And the range would be states. And then you just put all the values that's associated with it. All right, find the inverse. You're given a set of data here. Say domain and range of the function and its inverse. All right, so we know that the domains are the input values, and we have the input values are the x values here. So we'll just say, again, the original function here And we'll just go ahead and say the domain and the range. The domain of the original function right there, you have -5, 3, 0, 2, 7. The range of the original function would be the y values 1, 3, 0, -4, -8. Alright, so we wrote out the domain and range of the original function. Now the inverse function, the domain and range of the inverse function, let's do this. We know that the domain of the inverse is the range of the original. So domain of the inverse, we're going to take the range of the original, 1, 3, 0, -4, -8. Range of the inverse is the domain of the original. Now you sound real mathy, you know what you're talking about. You're starting to speak math. Welcome to the club. Alright, let's move on up a little taste. Is that all I want us to do? There we go. Alright, verify that the inverse of g of x equal x cubed is cube root of x. Alright, now you can verify this by using what we learned last time, taking the compositions, and if the compositions come out to equal x, then they're inverses. Alright, in a moment, what we're going to do is find the inverse function. Alright, so we're going to take these quick compositions. G of g inverse of x. Alright, so we're going to input g inverse of x inside of g. And g inverse of x is cube root of x. Cube root and cube power, they undo each other and simply leaves you with whatever is under the radical, x. Alright, on the other side, we're going to just, again, take the composition. This time we're doing with the inverse composition on the outside and the original. The inverse function on the outside and the original on the inside. So then you have the cube root of g of x. Again, cube root and cube power, they undo each other, and you're left with what's under the radical there, x. So those two are inverses of each other. And you do a similar thing for part B. We'll take f of f inverse of x. Then put the inverse function inside of the original. So we have 2 plus 3. Wherever we see the x is where the inverse function will go. That's 1/2 times x minus 3. Two times 1/2 leaves us with 1 times x minus 3 equals x minus 3 plus 3, and you have x. And this time we're going to put the inverse on the outside, put the original function on the inside, 1/2. Wherever the x is, that's where the original function would go. 2x plus 3 minus 3 equals 3 minus 3 is gone. Left with 1/2 times 2x equal x. So these are inverses. Now the rules for finding an inverse. To find an inverse, so we went through how to find an inverse from the data, and now we want to find it algebraically. Find an algebraically determined inverse. Algebraically determined inverse. All right. So there's several things that you can do. It's completely up to you. But this is what I like to follow. First thing first, you rewrite f of x as y. Then you swap them, meaning swap x and y. Then solve for y. You do this every time. Once you got y by yourself, by itself, that's your inverse. All right, so first thing first, rewrite f of x as y. Y equals x cubed minus 7. So I rewrote it. Next thing I'm going to do is swap x and y. X equal y cubed minus 7. So I swapped x and y. Now, the final thing said it said to solve for y. So I'm going to get y by itself. So I'm moving stuff around. All right, I'm going to bring the 7 over. I have x plus 7 equal y cubed. Y is not solo yet. So I'm going to do a cube power, I cube root. I do the same thing to both sides to maintain balance, maintain equality. So we have cube root of x plus 7 equal y. We got the y by itself, so our inverse function is f inverse of x equals cube root of x plus 7. All right, almost there, team. Ooh, almost there. Rules don't change. Here we go. Write f of x as y. Y equals 2x plus 1 over x minus 1. Now this x does not equal 1 right here. All that is telling you the domain of this function. That is all it's saying. The domain can be any number except for x equal 1. All right, back to our problem. Swap x and y. Go ahead and swap x and y. We have x equal 2y 2y plus 1 over y minus 1. Now again, solve for y. All right, so we have x times y minus 1 equal 2y plus 1. You're going to have to distribute, move stuff around because you want y on one side only. All right, so we have xy minus x equals 2y plus 1. We distributed the x throughout that parenthesis. Now I'm going to move all the y's to one side and everything else to the other. So this first term has a y, so it stays. This does not have a y, so you got to go. You got to go over here. So we have xy equal 2y plus 1 plus x. Is everything that has a y on one side? No, you got this. So rebel 2y need to go over there with your family. You got to go over there, and the way you move over there is by subtraction, right? So we have xy minus 2y equals x plus 1. Now check this out. Going back into your early algebra skills, learning how to factor. If these two have a y in common, if I pull out the y, if I pull out this y, and let's say we make this y, let's say we make this y red. If I pull out the y, I'm going to be left with a blue x, a blue negative 2. Equals, oh, I didn't mean to do that. Equals x plus 1. Now we have y times x minus 2. We want to get y all by itself. Divide each side by x minus 2. And we have y equal x plus 1 over x minus 2. Your inverse is f inverse of x equal x plus 1 over x minus 2. All right. Finally, last example of the day, hardest one yet, so get yourself ready. Find the inverse of a domain restricted function. This simply says your domain is going from 0 to positive infinity. So we have y equal f of x equal x squared. Let's go ahead and find this domain. I'm sorry, find the inverse. So we have y equal x squared. Undo. Are we undoing immediately? No, we got to swap x and y. Man, I thought y'all was gonna let me get by with that one. So we have x equals y squared. We swapped x and y. Now we're going to undo to get y by itself. And we have square root of x equals y. Your inverse function, f inverse of x, is equal to square root of x. I thought you said it's going to be hard. Game changer.